So, hello everybody. Welcome to Nonlinear Optics again. We'll be talking about the nonlinear refractive index today. It's pretty much for the first time, it's a third order nonlinear process. And as compared to what we had so far, where we basically generated a new color from two other colors. So in the simplest case, a monochromatic color from two other monochromatic colors. This is a little bit different, and you'll see that we'll notice some effects on the one hand on the beam profile of the radiation that we are using, and on the other hand on the spectrum. And actually it will be possible to broaden the spectrum. So if we use a short pulse, then of course it has a finite spectral width, and based on this nonlinear refractive index, we'll see that it's actually possible to broaden this spectrum and therefore provide the option to produce even shorter pulses. But this is the topic of the next lecture. This lecture is on the spatial things, so self-focusing in particular. Let me go back a little bit to the very beginning of this course. So what I have here on this slide is chapter 2, the first page of chapter 2, and you see that we expanded the polarization here in the second order term and then in the third order term. And and then we went on when we discussed third order processes. There we took this this term here from this expansion of the polarization, and we just plugged in here the simplest case where we just have one color in the fundamental, so one fundamental color, just one field, and then we took the cube of that and used some trigonometric identity, and we found a polarization that oscillates at the third harmonic. This is what we certainly expected, but what we also realized was that there is a polarization that oscillates just at the fundamental. And now if you go back to the very beginning, not just chapter 2, but just chapter 1, then you notice that that we actually said that the polarization that's oscillating at the fundamental, that's oscillating at the frequency omega, that this gives rise to the refractive index. And therefore, it's a pretty obvious conjecture to say that this now intensity-dependent polarization that oscillates at frequency omega at the fundamental, that this will lead to an intensity-dependent refractive index. And this is actually pretty much of this is the essential part of everything that comes for the rest of the course. May it be self-focusing today, then self-phase modulation in the next lecture, and in the final lecture even solitons. Yeah, so this is here at the basis of all these effects, and therefore it's so important. Okay, perhaps just another quick glance at what we had here. Yeah, so you see already kind of an idea on how the refractive index here should depend on the susceptibility. So you may remember this prefactor of 3/4. We'll come back to that just as a side remark later then. Okay, so with this, I would start with the headline. Actually, I put it down already. So intensity-dependent refractive index, self-focusing, and filamentation. So just as to write this up, what we just discussed. Yeah, so in chapter 2, we saw that the nonlinear polarization for third-order processes has a frequency component oscillating at the fundamental, oscillating at at the fundamental, that's right. Yeah, and therefore we expect, similarly to chapter 1, for first order processes, for linear processes, a contribution to the refractive index, and of course it will be intensity dependent, this contribution to the refractive index. And we can distinguish, of course, two cases. The first one I already mentioned. This is the so-called degenerate case, where all three input fields are equal, are the same. And then there's the non-degenerate case, where these fields are different. And there you can distinguish, in addition, the case where all fields, all beams come in the same direction, or where they come from different directions. And if they come from different directions, then actually they may have the same frequency, but they are nevertheless distinguishable. So we will distinguish two cases, but actually in this lecture I will only cover the first one, namely the degenerate case, and you may look up the non-degenerate case in the script, because, well, the derivation is pretty much the same. So we will distinguish two cases, the degenerate case which means all input frequencies, all three input frequencies I should rather write waves. Yeah? So I always speak of frequencies, and what I mean is always waves. Yeah? Why do I speak of frequencies instead? Well, because we, in our formulas, in our equations, these waves mostly appear just by their frequencies. So this is a little bit of jargon, but I hope you are okay with that. So all three input waves are the same for the degenerate case. Now, in other words, there's just one, and the other case, where these three waves differ in frequency and or direction. Yeah, in one word, in the wave vector. Well, in either case, the nonlinear polarization is, of course, given by the term that we already saw in this reminder with which I started this lecture. Yeah, so in either case, we have for the nonlinear polarization, so for the third order nonlinear polarization, so the tilde once again indicates that we are in the time domain and that we have the full temporal dependence. But that's not so important here at this moment. So we have the third epsilon 0 times third order susceptibility times the electric field to the third power. So that's our equation 1. Well, and then we would decompose, of course, this input field in different colors if we discuss the non-degenerate case, but as I said, we'll discuss the degenerate case. Yeah, one other remark here. So the intensity-dependent refractive index, will lead, well, of course, to a change in the refractive index as the intensity changes, and therefore it will affect the phase of the fields. So the intensity-dependent refractive index changes the refractive index n in dependence, or as a function, let's write, as a function of the intensity I, and the consequence will be that the phase of this field is modified, is modulated. The phase of all waves will be modified or modulated. And this is true in time and in space. So in the temporal and or spatial domain. So now let's try to derive the nonlinear refractive index. So we'll look at the degenerate case here and derive the nonlinear refractive index. So this is chapter 9.1. Derivation of the nonlinear refractive index, and it gets a name, so it's called N2. Derivation of the nonlinear refractive index for the degenerate case. Don't like this result, so here it's nicer. Okay, so for the degenerate case, it's clear what to write for the field. Yeah, so here we have just one field. And this means that E of t is given by E of omega e to the minus I omega t plus the complex conjugate. And now what we have to do is, according to this equation 1, we have to take the cube of that. Yeah? So this would be the second point here. According to 1, we need the cube of that. And this is just stupid calculation. And in order to save some time, I just copied that from the script, and here you see it. Yeah, so this is also what you have in the script. And what you see is that I wrote it 3 times, the product of 3 times this thing here, and then I multiply these 2 here, this gives this here, and in the next step I would multiply this result here with this remaining term here. And then I get these 6 terms here, and you see already that there are some that depend on the cube here. So oscillate with 3 omega, so this will be third harmonic generation, of course. And here this is just the complex conjugate of this one here. And similarly, we have here these 2 terms, the remaining terms, they all oscillate here at the fundamental frequency. And we can write this here for short in the following way. So we have E3 e to the cube, and then the third harmonic generation, plus the complex conjugate. So this here is just the complex conjugate of that, plus, and now 3 times E times the complex conjugate times E, and then E to the minus I omega t, and the rest is again just the complex conjugate of this term here, of course. And now we can compare this with equation 1 and find immediately a term for that will lead us actually to the nonlinear refractive index. Okay, so what we would do next is, so that's equation 3, we compare with equation 1. So what follows is just that P3 as a function of omega, so of the fundamental, is 3 times, and so this factor 3 comes from here, epsilon 0 times chi 3 times E of omega, and then the complex conjugate of that, and again E of omega. And you know, of course, that if I multiply the field with its complex conjugate, then I get a quantity that's proportional to the intensity, so I get the magnitude squared of the E field. And now if you compare this result here with what we had in chapter 2, then you will notice that there we had, instead of this factor 3, we had 3 over 4. And the reason for this is that back then in chapter 2, we used just a real field. So you see this indicated with the script E. So we used an explicitly real field, whereas here we use complex notation, and we use complex notation in an awkward form. So you know that we use complex notation in nonlinear optics. Pretty much all books use it this way. We write, as you see, for example, here in equation 2, we write this as the sum of this complex expression here plus its complex conjugate. But what we should have done would be to write here 1/2 of that, right? Think about Euler's formula, then it's clear that strictly speaking, there should be this factor 1/2. And if we would have put that, then we would have gotten the same result. And to be honest, this result is actually the right result. Yeah? So one always has to know how to read nonlinear optics literature. So I'm sorry about that. I would never have done it that way, but people do it like that since 60 years. Yeah? So, and all the books, almost all the books do it like that. Okay, so we note this as a remark. Yeah? So in chapter 2, we found 3/4 as a prefactor. The reason is that there we worked with explicitly real fields. So no opportunity for awkward definitions, for questionable conventions. Whereas here, we use E of t, so the explicitly real field is equal to, well, in principle it should be 1/2, but we actually don't do this, so we leave this factor 1/2 out. Which is questionable. Okay, well, let's continue and work our way towards the nonlinear refractive index. So we were talking about the polarization that oscillates at the fundamental frequency, and of course there is still the linear part. So we also, so if we talk about the refractive index, then this will certainly still be the dominating part. So we also have to, to talk about this. Of course, there is still the linear part of the polarization. And this linear part is given by, we call it P1 of t is equal to epsilon 0 times chi1 times E tilde of t. And if we now assume monochromatic radiation, as we did all the time here, then we find the same expression in frequency domain. So that's equation 4, and this here is equation 5. And then we can write down the total polarization. So the total polarization oscillating at polarization, oscillating at omega, at the fundamental. This is given by P total is equal to P1 of omega plus P3 of omega. And then we just substitute what we have in equation 4, for example. This is epsilon 0 times chi 1 times E of omega plus 3 times epsilon 0 chi 3 E of omega magnitude squared times E of omega. And you see a sum where in both terms we have E of omega, so it's obvious what we do next. We factor out E of omega, and then we get epsilon 0 times chi 1 plus 3 times chi 3 times the magnitude squared of the electric field times E of omega. Yeah? So and now if you compare this equation, so actually I call it 7. If you compare this equation with the one for the linear case, then you see that they look pretty similar. Yeah, so the only thing by which they differ is this factor. Yeah? So we find here, actually I should take this one because this depends on frequency, whereas this depends on time, but nevertheless it has still the same form. So what you see is that we just replaced this by this longer expression here, and so we may define an effective susceptibility. Yeah? So let's define that. The similarity of equation 5 and 7 suggests the definition chi effective is equal to chi 1 plus 3 times third order nonlinearity times, of course, the magnitude squared of the electric field, which is proportional to the intensity. So there's just a few factors of C and the refractive index and stuff like that. And accordingly, we would write the total polarization now in this form that really looks like equation 5. So we have epsilon 0 times the effective nonlinear susceptibility times E of omega. Now it looks like a linear equation, but it is of course not a linear equation because the effective susceptibility depends on the intensity. 8 and 9 here. Okay, so now really towards the refractive index. From optics we know the connection between susceptibility and the refractive index, and we'll now just use this. Yes, this is the reason why we defined the effective susceptibility, because we want to use this relationship that's known from optics. So from linear optics, or actually from a course in electrodynamics. So from electrodynamics, here in the second semester, I'll teach it again next summer. So from electrodynamics, we know that the refractive index squared, here it will depend on the intensity, but never mind, is equal to 1 plus the susceptibility, and here it's the effective susceptibility. And now we expand it again. Yeah, so we write it in its linear and nonlinear terms separately. So we have this relationship, and of course the message is, what we really remember is that this is equal to the ordinary refractive index. Well, of course I forgot here this term that's dependent or that's proportional to the intensity, and now I'll write down actually how it is connected to intensity. So this is 2 times n0 times epsilon 0 times c. Well, actually, the intensity is defined as that. Yeah? And then you can continue here and write n0 squared plus 3 times chi 3 times the intensity divided by 2 times n0 times epsilon 0 times c. So that's equation 10, I guess. Yeah. Okay, well, we are not quite finished here, because what we would like to have is an expression for the refractive index. And so far we have just a relationship between, well, the square of the refractive index. So therefore the idea is to use a power series expansion, considering that that the nonlinear term is much smaller than the linear term, at least for moderate intensities. Yeah? So we do a power series expansion. So 9. We use a linear expansion for n, or n as a function of the intensity, considering that the nonlinear part is much smaller than the linear part. That's true for moderate intensities. Of course, nowadays it's very easy to produce an intensity such that this is not necessarily the case. And then an entire new field of nonlinear optics starts, namely what some people call non-perturbative nonlinear optics. Previously it was called super intense fields, but nowadays super intense is perhaps relativistic intensities. So these things, of course, change as technology advances. So what we use is that n as a function of the intensity is approximated in this way, so that we have n0, the regular refractive index, and now here we introduce the nonlinear refractive index n2. Yeah? And now we take the square of equation 11, and we just substitute it in equation 10. Yeah? So substitute the square of equation 11 into equation 10. And what we have then is that n squared of the intensity is equal to n0 plus n2 times the intensity squared, and now we approximate this by n2 squared plus, of course, 2 times n0 times n2 times the intensity plus something that we neglect, namely the term that's dependent on the intensity squared. So this would be, let's write it down. We would have n2 squared times the intensity squared, and this we neglect. And then you can immediately solve for n2. What we find is that n2 is equal to 3 over 4 times 1 over n0 squared times epsilon 0 times c, and the third order nonlinearity. That's an important equation, so it's justified to frame it. Now it would be interesting how large this is, and now it depends on what kind of effect you are using. So typical values. And I have a table for that from literature. And indeed, depending on the mechanism, we have different things here. So if we look at electric polarization, so this is actually the thing that so when we don't say anything else, then mostly here in nonlinear optics, at least in the context of this course, we mean nonlinearities due to electric polarization. This is when the electron is driven by the electric field, and when this driving or when the electron motion is no longer harmonic. So this is what we always have in mind if we speak about nonlinearities. But it's by no means the only mechanism for nonlinear optics. So the nice thing about nonlinear effects due to electric polarization is that these effects are very fast. So response time here you see. So actually one should probably write that it's smaller than a femtosecond. So it's in the attosecond regime. And on the other hand, these effects are quite small. So this N2 is on the order of 10 to the minus 16 in units of inverse watts per square centimeter, right? So of course it must have this unit in order to give a meaningful result considering this equation. Well, another thing that you could do is to consider the alignment of molecules. So when you have a molecule, then whether your assume that this is a diatomic molecule, say nitrogen, oxygen, something, and then the refractive index for a polarization that's parallel to the molecular axis is different than for a polarization of the light that has that's perpendicular to the optical axis. Yeah, so, and it is, of course, possible to align molecules, typically with lasers. And then there are other effects, perhaps. This one here is kind of interesting, important, but actually pretty nasty, I have to say. Namely, when you have a high power laser, high average power, say, then, of course, there's always some absorption in any material, and therefore this material gets warm, say a lens or nonlinear crystal, heats up, and therefore it thermally expands, and this changes the refractive index. Yeah? And of course, the time constant of that is pretty slow, milliseconds or so in this regime. But the thermal effects, these nonlinearities, are pretty large. And moreover, they are non-local. What do I mean with non-local? If you heat up the central part of a lens, then of course the heat diffuses to all other parts of the lens sooner or later, and therefore the nonlinearity that you induce in one spot of your optical material will also influence the nonlinear properties at another position, at another place in this material. So it's non-local, so dealing with this mathematically is, of course, well, not always fun. Let's put it in this way. Okay, so this is the nonlinear refractive index, and we can also derive it for the degenerate case. I will just give here the result, because the calculation is actually pretty similar. So this would be 9-2, the non-degenerate case. And as I said, I'll just give the result. So the result is that for this cross modulation of the refractive index, this is twice as large. Instead of 3/4, we have just 3/2. But apart from that, it's the same. So with this, let's come to self-focusing. So I just give the idea, and then we'll have a break for 5 minutes or so. So the headline would read self-focusing. So the bottom line of the entire thing is that the change in refractive index by the laser beam will modify its own propagation through the material in question. So the modification of the refractive index by a wave will affect its own propagation. And now for laser beams we have the following situation. So if you look at laser beams, then you typically would have in mind a Gaussian beam where the intensity profile of the beam is a Gaussian function, therefore the name. But there are, of course, also other possibilities to shape a beam. So you can even produce a beam that has zero intensity on the beam axis, so it's donut-shaped. But nevertheless, for each laser beam, for each wave, there is a dependence of the intensity as a function of the distance from the beam axis. Yeah? And this means that if you propagate such a beam through a medium, this medium will have a position-dependent refractive index. Yeah? So all laser beams have a beam profile with varying intensity. Yeah, and this means the refractive index varies across the beam. And the typical situation is, of course, that on the beam axis that the intensity is highest, and we'll look at this case in particular. Yeah? So the typical situation is large intensity or high intensity on the beam axis and therefore the refractive index N is largest for the central ray. Yeah. And now just a quick drawing here. Yeah, so the situation is the following. And so what you see is that for the central array we have a large refractive index, and for a marginal array we have a smaller refractive index. And now if you remember, or if you think about optical path lengths, and perhaps even remember that it is possible to create a lens just with in a material where the refractive index has a gradient, then you see that we have exactly the same situation. Yeah? So you can compare actually this situation to a lens, yeah? Very simply to a lens. There also for the marginal array you have, well, shorter optical lengths in the glass, yeah, because also the geometrical length is shorter, whereas for the central array you have a longer optical path length. And this is the same thing here, right? And now it's obvious what we'll use next. We'll just use Fermat's principle, but this we'll do after a few minutes of coffee break. Actually, I have a tea here with me today. So the Max Planck School of Photonics presented me for Christmas with this thing here. First, I didn't know for what to use it actually in particular, but then I realized that's perfect here for this course because it's still hot. Actually too hot, I'm afraid. Okay, see you in 5 minutes. So, let's continue. Just noticed that my Zoom session crashed. So I hope it will revive at some point again, so that we have this feedback channel if something goes wrong here. Good. Let's pick up where we ended before the break. So we said the following. Yeah. So we had this situation here, and we said that we want to use Fermat's principle. So let's just do that. So obviously, Fermat's principle can help us to find so the self-focusing angle, the self-focusing angle. So what Fermat's principle says is that the optical path length is the same for all rays, and the optical path length would read is the integral over the path multiplied with the refractive index. And this should be constant for all rays. So I gave this equation the number 31. And what we do in order to derive this expression is to look at it just for the central ray and for the marginal ray. So we consider the central and the or one marginal ray. Right. For the marginal ray, we assume, of course, that the intensity is negligible, whereas for the central ray, it's the maximum intensity. So the marginal ray, there we have that n is just n0, and this leads to an optical path length for the marginal ray given by n0 times. Now I introduced this self-focusing length. So ZFF, self-focusing, divided by the cosine of this self-focusing angle. And similarly for the central ray. There we have that n is equal to n0 plus n2 times the intensity, and therefore the respective optical path lengths would be n0 plus n2 times the intensity times the self-focusing length. So this is equations 32 and 33. And of course they should be equal. And of course, you see that this is a pretty rough calculation that we are doing here. So what we do here is actually only valid at the entrance phase, as the beam here self-focuses. The intensity, of course, is increased, and therefore, one would have to do a much more complicated calculation, but you still can say that we are looking at this angle, right? And this is actually here defined at the entrance phase. Yeah? So just as a remark, 32, 32 is valid only at the entrance phase. Because the intensity will increase due to self-focusing. Increase due to self-focusing. But as long as we're only interested in theta self-focusing, it is okay. As we are only interested in theta SF, it is okay. Well, and if we are interested in more, then it's still an approximation. Yeah? But now we equate equation 32 and 33, but we do it using a power series expansion. So power series expansion. This means that cosine self-focusing is equal to 1 minus 1/2 theta self-focusing squared. This is equation 34. And now we really do what I announced several times. So we equate marginal optical path lengths of marginal and central ray, and then we get that n0 plus n2 times the intensity times the self-focusing distance is equal to n0 times the self-focusing distance divided by the cosine of theta SF, and there I would insert, of course, equation 34. But the nice thing here is that the self-focusing distance cancels out. And this is actually, so if you think about the remark that we just made, this is actually a good thing. So that the self-focusing distance that we would calculate with this, trivial approach, so what you would expect is that it goes like this, and therefore this is not really the self-focusing distance, but it actually cancels out. And after a few lines of trivial calculation, you find the self-focusing angle, and it's equal to 2 times n2 times the intensity divided by n0, right? Nice expression. So here you see, so the denominator, the numerator, so this is just the change of the, so what you have here is twice the relative change of the refractive index and the square root of that. 35. So, next point. We want to, so we said now that the pulse that this is that the pulse is focused, that this pulse self-focuses, so that its spot size gets smaller and smaller. But on the other hand, we know that that every beam also diverges due to its wave nature, due to interference finally, and so we can say, well, if I have a diverging beam and send it through some material with just the right intensity, such that the divergence is balanced by self-focusing, then you could say that this beam is self-trapped. And what we want to do is to calculate the power where this happens. So we want to calculate the power of the laser beam. I avoid the word intensity for a reason that will become clear later. So we want to calculate the power at which the self-focusing effect is just so strong that it cancels diffraction. And this is called the critical power. And therefore, the headline of this subchapter is Self-Trapping and Critical Power. 9.4, self-trapping and critical power. So we start with this well-known fact that every beam diverges. Every beam diverges. The smaller the beam size, the more. The longer the wavelengths, the more. You know this. Every beam diverges unless some focusing effects counterbalance diffraction. Focusing effects counterbalance diffraction. Here by self-focusing. The condition that we are interested in is that the diffraction angle is supposed to be equal to the self-focusing angle. Right? So we'll demand that both are equal. Well, there's actually another way to counterbalance diffraction, and this is used in optical fibers. There's basically total reflection, and actually you can look at self-focusing and self-trapping also in this way. And you also find it in the script. So we need an expression for diffraction, and what we assume is just the formula that you would have for a beam with a circular cross-section. So a familiar formula for diffraction is where you have this famous factor of 1.22, but here we just look at half the refractive, the diffraction angle, so we have 0.61. Then lambda divided by n0 times d, right? And d, if it would be a Gaussian beam, this would be 2 times this beam waist. So that's equation 40, and here 41. And well, now we just plug in the equations that we have. So we substitute this equation 35 and the equation 41 into this equation 40, and we already have an equation that will give us a condition. So what did I say? 41 and 35 in the condition 40. And then we find 2 times n2 times the intensity divided by n0 should be equal to 0.61 squared times lambda 0 squared divided by n0 squared d squared. Yeah, so this square is due to, well, the square root here in equation 35. And then we can solve for the intensity. Yeah, so we find for the intensity 0.61 squared times lambda 0 squared divided by 2 times n2 times n0 times d squared. Yeah? So, and now the point, or one of the points here is, well, this is of course a nice formula, nice and handy, but there is something very remarkable about that formula. And this you see here. So we have here this factor d squared. And here we have the intensity. And you know that intensity is power divided by area. But here we have also the area, at least a quantity that's proportional to the area. So what you see is that it's actually not dependent on the intensity, but it's dependent on the power. Right? Very strange. And very remarkable. What this equation says actually is that, well, that if your power is large enough, then you will focus. And you can't avoid it. You can't avoid the self-focusing effect by just expanding the beam, because the power remains the same. Right? So whether you have a millimeter-sized beam with a power of, say, a gigawatt, right? And if this is sufficient, then you can expand it to a kilometer radius, and it will still self-focus. Now you might think, this can't be. Well, it is this way, and actually there are other fields in optics. I think in this case particularly about relativistic optics, where you have the same property, namely that if the power is sufficient for relativistic self-focusing, it depends only on the power and not on the intensity. Yeah? But if you are now too confused, the point is, of course, that we just discuss the intensity that's necessary for the self-focusing effect to start. We didn't say something about the self-focusing distance. Yeah, so the self-focusing power, so the fact whether or not self-focusing happens is a completely different question from the question where the beam will collapse. Yeah? So if you want to avoid the beam collapsing, then you simply need to expand your beam. It will still self-focus, but your optical material will probably be shorter than the self-focusing distance. Yeah, so the only thing in order to avoid the collapse of the beam is to make the self-focusing distance long enough. We didn't talk about the self-focusing distance. We so far just talked about the power that's necessary in order to have the self-focusing effect. Yeah? So let's write that down. That's an important property. So the power P of a beam with intensity I is given by P is equal to I times A, where A is proportional to D squared, is the cross-sectional area of the beam. Yep, or in other words, P is equal to I times pi times D over 2 squared if you have a uniform circular beam. Yeah. So let's write here approximately, because if it's a Gaussian beam, then of course it's a question of definition, what you consider the area of the beam. But it is certainly, this proportionality is certainly valid. So what we then get here is P is equal to pi times 0.61 squared times lambda 0 squared divided by 2 times n2 and then times 4. Yeah, so from this factor here. So we have A times n0 times n2, and this is approximately lambda 0 squared divided by A times n0 times n2, and this is the so-called critical power. Equation 43. Yeah? It's not dependent on the beam diameter. Yeah? Beam expansion will not prevent self-focusing. Well, the final thing that we should do in this chapter would be to talk about the self-focusing distance. And the self-focusing distance will, as we discussed already, will certainly depend on the intensity and not only on the power. If you look in the script there, you find also a chapter 9.5. The number in the script is actually 12.5, where the critical power is derived in a different way, namely treating the effects that we just discussed as in the sense of a light wave. Yeah? So then you would make the same arguments that you do for an optical fiber, where you assume that your angle of incidence needs to be small enough in order to have total internal reflection. But we'll skip this here and rather go to the next subchapter, namely 9.6. Go away. So 9.6, the self-focusing distance. Good. Well, if you look back to our figure, so I get it once again here, then you immediately get an idea what to do. So we can immediately derive or write down an estimate, at least, for the self-focusing distance. So we just need to multiply the angle. So we just need trigonometry. So from or at the figure we see that this waist here, so W0, you see it here, so that this is connected with the self-focusing distance and the self-focusing angle in this way. And then you can, of course, write that the self-focusing length is given by the radius of the beam divided by the self-focusing angle. And then we can substitute the expressions that we found. In particular, we can substitute equation 35, namely the equation for the self-focusing angle. So let's do that. So using 35, which is the expression for the self-focusing angle, we find that the self-focusing distance is W0 times N0 times 2 times N2 times the intensity. And here you already see that it does depend on the radius. And okay, well, I take back this. So we have W0 times the square root of N0 times the square of the beam radius times pi divided by 2 times N2 times the power. So I substituted the intensity by the respective expression for the power. So that's 51. And now we can also express this in terms of the critical power, so that we say, well, when the power is, say, twice the critical power, then the self-focusing distance is this and that. So in terms of the critical power, there we would find, so we just expanded by this by the critical power. So we would do the following. So we have W0 times N0 times W0 squared times pi divided by 2 times n2, and then we write 1 over the square root of p divided by the critical power times 1 over the square root of the critical power, right? And then we find 2 times W0 squared times N0 times the square root of pi divided by lambda 0, and then we have 1 over p over the critical power and the square root of that. Yeah? This is okay as long as we neglect diffraction. If we want to include diffraction, then, well, we have to find an expression for the angle that includes both, namely the self-focusing angle and the diffraction angle. And we do this for a Gaussian beam. Yeah? So if we include also diffraction, we can write for a Gaussian beam that theta is equal to the self-focusing angle squared minus the diffraction angle. Yeah, so already assuming that the self-focusing angle is larger. Yeah? And this means, of course, take the square of that, and I get this equation here. Equation 53. Yeah? And now we plug in equations here. And we find that the self-focusing distance, again, with this ansatz here, W0 divided by theta. And now we substitute everything that we derived so far, and what we get is W0 divided by 0.61 lambda 0 divided by 2 times N0 W0, and then 1 over, yeah, pretty ugly, 2 times N2 times the intensity, N0 times N0 squared, times 4 times W0 squared divided by 0.61 squared times lambda squared. Sometimes I write lambda 0. Let's write lambda 0. So like this. Yeah? Again, we want to have it in terms of the critical power. Yeah? So in terms of the critical power, and I just give the result. Yeah, so the it's a trivial calculation. There we get 2 times N0 times W0 squared divided by 0.61 lambda 0, 1 over the square root of the power normalized to the critical power minus 1. That's equation 54. Good. So with this, we are done for today. Pretty much in time. Next lecture, we will look at, I said this already, we'll look at the effects that the intensity-dependent refractive index has in the temporal domain. So just as a teaser, think of the following, that we have a short pulse like this. Yeah? So here, this is time. Oh, this is time, and here we have intensity. Yeah? So what it means is that, well, of course, that the intensity goes up as a function of time and goes down again. But this also means that the refractive index goes up and goes down again. Right? And it's, of course, very interesting how self-phase modulation affects the beam propagation. And in order to study that, the nonlinear Schrödinger equation is particularly useful. And this is the reason why I prepared a script where I discuss linear pulse propagation and where I derive the respective differential equation. It's sometimes called a Schrödinger equation. So you all know from a basic quantum mechanics course that a wave packet, that a quantum mechanical wave packet, that this disperses. And we have the same effect in optics when you have a short pulse and you send it through some glass, so through some material that has dispersion, then the pulse gets in general broader. And all these things I discuss in the script, and in particular I derive the respective differential equation, which has the form of a Schrödinger equation. And now if we include the effects that we discussed today, the nonlinear index of refraction, then this equation is of course modified a little bit. And it again has the shape of a Schrödinger equation. Actually, this time a Schrödinger equation that also has this potential term. All right, so potential times the wave function. But in our case, this potential term depends actually on the wave function, so which in our case is of course the electric field. Yeah? So in quantum mechanics, we have the wave function psi. We have the temporal derivative on the left-hand side. Then we have the second spatial derivative as the first term on the right-hand side. And then we have the potential times psi. And in nonlinear optics, we have the same thing, just not psi, but the electric field as the pulse, as the wave function. We have the second derivative of that, and then we have the potential term. But the potential term now depends on the electric field itself, or rather its magnitude square. And therefore this equation is a nonlinear Schrödinger equation. It has nothing to do with quantum mechanics, as I said already. Right? In quantum mechanics, there is no nonlinear Schrödinger equation. But this one has, of course, the shape of a Schrödinger equation, therefore it's called nonlinear Schrödinger equation. But once again, has nothing to do with quantum mechanics. What I'll do next in the next lecture is to quickly derive this nonlinear Schrödinger equation, very quickly, because I assume that you know how it is done in the linear case, and we just do the same steps for the nonlinear case, and we immediately have it. All right, so I will present this in a very quick way, and you have to look at the script if you don't know this material already from a course in linear optics, say a course on short pulses. You have to know this material in order to be able to follow. So please look at it. And as a final sentence, tonight or later this afternoon at 5 p.m. there will be another short Zoom session for questions and answers if you're interested. It's entirely optional. This Zoom session broke down and didn't come live again, but I hope that it works better tonight. With this, thank you for your attention and see you either tonight or next week. Thank you.